Good day everyone, I am Jinlupi Abad from Section Q and I'm going to report Chapter 17, which is the Soil Engineering for Highway Design. This chapter presents a summary of current knowledge of the characteristics and engineering properties of soil that are important to highway engineers. So, highway engineers are interested in basic engineering properties of soils because soils are extensively used in highway construction. Soil properties are of significant importance when a highway is to carry high traffic volumes with a large percentage of trucks. So, we will be talking about the soil characteristics from its origin, formation, grain size, and its shape. So, origin and formation of soil. Soil is basically a loose mass of mineral and organic materials that cover the solid crust of granitic and basaltic rocks of the earth. So, soil is mainly formed by weathering and other geologic processes that occur on the surface of the solid rock at or near the surface of the earth. Weathering. Weathering is the result of physical and chemical actions, mainly due to atmospheric factors that change the structure and composition of the rocks. So there are two types of weathering, the physical and the chemical. Physical weathering, sometimes referred to as mechanical weathering, this causes the disintegration of the rocks into smaller particle sizes by the action of forces exerted on the rock. While the chemical weathering, this occurs as a result of oxidation, carbonation, and other chemical reactions that decompose the minerals of the rocks. So, our soil is described in two types, the residual soils and transported soils. So, residual soils are weathered in place and are located directly above the original material from which they were formed, while the transported soils are those that have been moved by water, wind, glaciers, and so forth, and are located away from their parent materials. So, there are geological history of any soil deposit, and this has a significant effect on the engineering properties of the soil. So the first one is sedimentary soils. So these soils, which are formed by the action of water and are usually particles that have settled from suspension in a lake, river, or ocean. So these soils range from beach or river sands to marine clays. Then we have the oilian soils. These are formed by the action of wind and are typically less. So less is described as the yellowish-brown loamy deposit which is found in North America, Europe, and Asia. So, it is believed that these loams are chiefly deposited by the wind. So, their voids are usually or partially filled with water. And when it's submerged in water, the soil structure collapses. So soils also may be described as organic when the particles are mainly composed of organic matter, or as inorganic when the particles are mainly composed of mineral materials. So surface texture mainly on the shapes and sizes of the soil particles and their distribution in soil mass. For example, soils consisting mainly of silts and clays with every small particle sizes are known as fine textured soils, whereas soils consisting mainly of sands and gravel with much larger particles are known as coarse textured soils. So the individual particles of fine texture of soils are usually invisible to the naked eye, whereas those of coarse textured soils are visible to the naked eye. Then, coarse-grained. Coarse-grained soils are sometimes defined as those with particle sizes which is greater than 0.05 millimeter, such as sands and gravel. So, fine-grained soils are those with particle sizes less than 0.05 millimeter. So, the example of these are silts and clays. So, the dividing line of 0.05 millimeter, which is 0.75 millimeter has also been used is selected because that is normally the smallest grain size that can be seen by the naked eye. Since there is a wide range of particle sizes in soils, both the coarse and soils, and fine-grained soils may be further subdivided, as will be shown later under soil classification. So, sieve analysis, sometimes known as mechanical analysis. So, this is used to conduct on a sample soil to determine the distribution of particle size in soils. This is done by shaking a sample of air-dried soil through the set of sieves with progressively smaller openings. So, we have different sieve that we have a sieve that has different numbers and millimeters. So there are several others with openings increasing up to 125 millimeter or 5 inches. Then for soils containing particle sizes smaller than the lower limit, the hydrometer analysis is used. A representative sample of air-dried soil is sieved through the number 10 sieve, and a sieve analysis is carried out on the proportion of soil retained. This will give a distribution of coarse material. A portion of the material that passes through the number 10 sieve is suspended in water, usually in the presence of the flocculating agent, and is then left standing until the particles gradually settle to the bottom. So, a hydrometer is used to determine the specific gravity of the suspension at the different times. The specific gravity of the suspension after any time, or T, or represent as T from the start at the test, determine the maximum particle sizes in the suspension as D, which is the maximum diameter of particles in suspension at depth Y, is equal to the square root of 18 times the coefficient of viscosity divided by the unit weight of soil particles minus the unit weight of water multiplied by the density over time. So we have here the percent finer by weight or mass and the grain size. So this figure shows the distribution of particle size in different soils. So the natural shape of a soil particle is either round, angular, or flat. So round particles are found in deposits of streams and rivers and have been subjected to extensive wear and are therefore generally strong. Flat and flaky particles have not been subjected to similar action and are usually weak. Fine-grained soils generally have flat and flaky shaped particles, whereas coarse-grained soils generally have round or angular shaped particles. So, angular shaped particles have more resistance to deformation than those with round particles, since the individual angular shaped particles tend to lock together, whereas the rounded particles tend to roll over each other. So, the basic engineering and properties of soil. So, we will be talking here about the phase relation, the Atterberg limits, and the classification of soils for highway use. So, phase relation. A soil mass generally consists of solid particles of different minerals with spaces between them. So the spaces can be filled with air and or water. Soils are therefore considered as three-phase system that consist of air, water, and solids. So as we can see here, we have a figure that shows the weight of air, the weight of water, and the weight of soil. So this weight of water can be considered as the voids of air, voids of water, and voids of soil. And we have the void of volume. Then we have porosity. Porosity is the relative amount of voids in any soil and is in a soil that is important quantity that influences some aspects of soil behavior. So this amount can be measured in terms of the porosity of the soil, which is defined as the ratio of the volume of voids to the total volume of the soil and is designated as N. So we have here the equation of N is equal to the volume of voids divided by the volume. So void ratio. Void ratio is the amount of voids that can also be measured in terms of the void ratio. So it is defined as the ratio of volume of voids to the volume of solids and is designated as E. So here is the equation. So if we are going to sum up the equation of the porosity and the void ratio, so we will come up with E is equal to NB over volume of solid, which is equal to N over volume of solid times Vs plus V, which will be equal to N times 1 plus E. So by getting N, we will have N is equal to E over 1 plus E. Then for the void ratio, we have E is equal to N divided by 1 minus N.